Okay, good afternoon. Let's continue on formation damage. Let's quickly cover what we have studied. Can you hear me?
Yes.
Okay, let me share the slides as well. Okay, can you see the slide? Is the slide gone through?
Yes, it's okay.
Okay. So last time we talked about importance of the fluid loss. It means the drilling fluid lost into the formation. What is bad about that? First of all, formation damage, and because as much fluid we lose into the reservoir, into the formation, the more depths of the formation damage, the more severe the formation damage, and on the other hand, we lose the expensive material, which is the drilling fluid, because it has various chemical compositions that are also expensive. So, and the fluid loss rate is controlled by properties of the filter cake that is created by the drilling mud solids on the reservoir pore throats at the entrance into the reservoir from the wellbore. It depends on formation porosity and permeability, how long it will go deep into the formation. Whole time, how long we will drill through the reservoir part, overbalance, the degree of the overbalance, or how much pressure is exceeding, for how much pressure the wellbore pressure is exceeding the reservoir pressure, and borehole dynamics as a high circulation rates, mechanical damage when you do a round trips or change to BHA. The filter cake is, as we said, created on the pore throats, not allowing the further mud fluid to go into the reservoir formation. And if this filter cake is created as a screen on the wellbore wall, then it is a good filter cake because full pore space are protected from the invasion, the solids invasion into the pore space. If we get this bridging effect or screen effect inside the formation, then that means we will get some formation damage by solids, precipitations due to the interaction between the mud fluid and formation fluid. Good filter cake is created with the, it should be thin but impermeable skin on the wellbore, and it is achieved by using a wide range of particle size, solid particles sizes in the fluid mud, because the different particles, various particle size will create a the permeability of various particle size always is less than the permeability of well-sorted, well-rounded grain size or particle size. So therefore, we are looking for wide range of solid particle size in the drilling fluid. Here you can see the range is from 0.1 micrometer up to the 100 micrometers, and then the kind of filter cake formation. To create a good filter cake, we need to follow the rules that when the diameter of the particles should be more than 30% of the or 1/3 of the pore throat diameter, and in that case the filter cake will be formed on the surface of the formation or between the formation and the wellbore, and it can be removed by backflow or acid wash, which we'll learn in next chapter, and may require sufficiently long perforations. So if the smaller particle size for the drilling fluid in the drilling fluid will make the those particles, those solids, grow into the formation, bridging inside of the formation, and if the particle size are too small, then there will be no filter cake, and the particle will go through the pore size formation without causing deformation damage. This is the invasion profile depending on the rock porosity and permeability. As we said, higher the rock permeability, the longer the penetration of the solids and filtrate of the drilling mud. And these are the different drilling mud or mud fluids, the different effect of drilling mud. And as you can see, the oil-based mud has a less damage risk, but it costs much more than the fresh water or any water-based mud. This is the we learned at which stage of the drilling, at which phase of the drilling we have more fluid invasion volume into the reservoir, which is the most. It goes into the reservoir when we drill through the reservoir, and the reservoir is against the opposite drill pipe. So what the effect of drilling fluid loss into the reservoir is the increasing water saturation, addition of extra phase will cause change in relative permeability, a viscous emulsions, when the water oil emulsions having high viscosity will block the pore passes, fluid passes through the pore space, and changing wettability again will cause a change in relative permeability. There is also polymers are included into the mud fluid for different reasons. may be absorbed by the formation rock minerals. Of course, particle migration and or clay swelling will be also another reason for the formation damage or reduced permeability. And due to the incompatible fluids, we may have some precipitations in the reservoir in the formation, which will again mechanically reduce the permeability of the formation. So these are the demonstration of different. Here we have a water block after the invasion. Before damage we have full continuous oil phase, but then the saturation changed and we have a water blockage of the oil passes. The third phase, when we have it's especially important for the gas reservoirs, when we have oil or oil and water emulsions in the droplets in the pore spaces, that might cause relative permeability for gas reduced significantly. Emulsions, as we said, polymers and fine migrations, reducing the pore throats size going through the formation and reducing permeability. Clay swelling, when the depending on clay chemistry and morphology and the chemistry of the mud fluid, these clay minerals in the reservoir may start swelling, and it will reduce the pore throat size or pore space, reducing permeability as well. Therefore, we, as we said, for the very high permeability rocks or fractured formations, it is very vulnerable for the formation damage, and therefore we may use underbalance drilling, but keeping in mind that we have to also keep the well stability, well bore under control to avoid any blowouts or any undesirable these consequences. Then we talked about the damage in horizontal well, and we learned that horizontal wells are more prone to formation damage because of longer distance to drill and in the horizontal space, and it is not a uniform because the hill part of the horizontal section is more exposed to the longer time of the mud contact, and this part will be even more damaged. There is also effect of lateral heterogeneity, so it might be this profile of the formation damaged zone might be completely different. So it's therefore the conventional Hawkins formula may not be applied in this zone, also because of the anisotropy, when we have a great effect of the vertical and horizontal permeability ratio, and the so the summarizing drilling mud type, formation properties, open hole time, pressure over balance, borehole dynamics are affecting or controlling the fluid loss or formation damage due to drilling, and these are the how mechanism formation damage due to the drilling. And today we'll talk about the cementing and perforating drilling formation damage due to the cementing and perforating. As you know, before we run cement job, we inject some washers and spacers to clean the wellbore, to make to provide smooth operating conditions into the wellbore, and this will be destroying the mud cake, and so the contact with the reservoir is open, and fluid invasion will start. However, this invasion will be not so deep because of the limited amount of the limited volume of the injections, because we inject just to clean the wellbore, and then the cement slurries fluid loss is more dangerous, because by losing the cement slurry into the reservoir, we will create even higher or severe damage to the reservoir, and we may have precipitations of calcium carbonate due to the calcium carbonate and the calcium silicates reaction with the mud fluid, so the cementing fluid. We may have some precipitations. Also, fluid loss in the cementing is very important, because, well, control of the fluid loss is very important, because if we lose the fluid into the reservoir during the cementing operations, then that is causing, again, unsuccessful cementing. That means our cement job is not failure of cementing, and that will create a very severe consequences during the production, to isolate, especially for isolation jobs, especially if we have water bearing layers above or below the reservoir, and that means we may have channeling effect when the so-called third-party waters will be channeled into the wellbore, so we will lose the well productivity in very short time. So therefore, for the cementing success, fluid loss control is even more essential. And of course, for the gauge hole, when we have this type of gauge hole, then the perforation design is very important, because we have to understand, we have to make a design of the perforation in a way that the perforations bypass the deep damage area or cementing sheets, so the wellbore is connected to the original reservoir part, original reservoir permeability zones. Is there any questions so far? Is everything clear? Hello?
No questions so far, Ahmed.
Okay. So then let's continue again. Gauge hole is the hole when it's called when we have a washed zone around the wellbore, and in this case we have to fill all this area, all this zone with the cement, and then perforations should be bypassing this cement sheet and damage zone through to clean reservoir permeability part. Damage due to the perforations should be cleaned up by the perforating with underbalance or extreme overbalance conditions, and it's also cleaned by producing back the completion fluids and the at high rates, high drawdowns to clean the from the perforating tunnels from the perforation debris from the crashed materials of the reservoir. So we have clean perforation tunnel and good connection between the reservoir, undamaged rock, and the perforation. So it can be again removed by the backflowing, acidizing, underbalance perforations to flow back into all these materials or crashed rock materials from the perforation tunnel into the wellbore and produce up. The formation damage during production may be is caused by first the fines movement, because as we produce, we change the stress in the reservoir, we change the pore pressures, we depending on the viscosity of the moving fluids or reservoir fluids, we may have exceed the dragging forces and detach the fines sand particles, small sand particles from their original point, and those fines will start moving, will be mobile inside of the pore space, and at narrow pore throats they will be collected and bridging the flow passes. Another is using incompatible workover and injection fluid may cause the precipitations in the reservoir. It might be some emulsions created again, and that will change the permeability around the wellbore. Again, because of incompatible fluids and changing the pressure and temperature regimes in the reservoir and near wellbore zone may cause or may trigger the scale formation, both in the formation and in the tubing in the wellbore. That will reduce the flow path, and by that obstructing the flow of the fluids to the surface by hence reducing the productivity of the well, and pressure reduction leading to introduction of the third phase. What does it mean? Somebody could explain me. Pressure reduction leading to introduction of third phase. We have covered this earlier in previous semester. So what would it mean? Which type of third phase is meant here?
For example, we want to extract oil or gas, and after pressure reduction, water can flow to the wellbore. I think third phase here is water, if I'm not mistaken.
Water is always second phase.
Maybe solid particles from the sand production may come into the tube, and it would call as a third phase, as a solid phase.
Well, we considered it as a fines movement.
Pressure is below the bubble point, and that's the introduction of gas of the third phase.
Okay. What else?
Equally, if we apply too much drawdown, I mean, not, let's say, not bubble gas induced gas, but gas cusping may take place from the gas cap, I mean, and that will be another introduction of gases of the third phase, actually.
Okay, what about the gas reservoirs? What can happen with gas reservoirs?
We may have condensate blockage in gas condensate reservoirs. When pressure falls, we know that heavy fractions, they just drop out.
It's called condensate banking.
Condensate, yeah.
It's called condensate banking. Yes, so the pressure reduction when the pressure in the formation in near wellbore zone goes below the bubble point or the dew point of the gas. What happens in oil reservoirs, gas is dissolving from the solution and occupying the pore spaces that were occupied before the oil, and that will change a relative permeability to oil. In gas reservoirs, the condensate will drop out of the gas, and that will again create a blockage of the pore sizes, pore throats before occupied by the gas. And gas condensate, condensate banking is even more severe damage than the gas dissolved out of the solution. So as we cleared, this point is about having gas in the oil pores, oil space, or gas condensate banking in the gas reservoirs. And well stimulation is always danger for the damage because we have a different chemical composition for the well stimulations, or the for hydraulic fracturing we have slurries to deliver. We have to inject water and then slurries to deliver propans, and that are also, although we are stimulating, but this also will carry some formation damage because of the chemicals, chemical composition, incompatibility, and high pressure injections. Okay, so fines movement, as we talked, it is especially it is effective when we have a connate water and the some fines are immobile within this connate water, and when the water breaks through the reservoir through to the wellbore, then this connate water becomes part of the flow, and these immobile becomes mobile and can cause blockage of the pore throats. This is the formation damage due to the incompatible workover and injection fluids, and effect of a volumes and measured core permeability. So depending on the permeability of the reservoir, we can unrated surface water, we can inject very small amount, but if we filtrate the surface water from the solids, we can inject much more water through the perforations. So that's how the cleanliness of the workover and injection fluids affecting the injectivity or formation damage. Chemical compatibility, again, it's a different portions of composition of concentration of various chemicals, and as you can see, they have different pore volumes, flow depending on the permeability. Completion fluid effect, it is an example from a Nubia formation, one of the oil fields. So you can see that the completion fluids, how the completion fluid affected the results of the workover. Here you can see using diesel, production loss was maximum in the calcium chloride and filtered seawater, because those have a chemical effect, chemical interaction with the reservoir fluid and reservoir formation, rock minerals, and therefore the decline in the rate was with the filtered seawater, it was even 100%, so the water didn't flow at all after the workover completion. Formation damage, scale formation, you know, we talked about that when we have a lower pressures and temperatures, organic and inorganic mineral deposits starts on the tubing or the flow path in the formation, and these can substantially reduce the flow path even in the tubing, you can see, or can block the flow totally completely, so no flow will be through, and therefore there are some inhibitors used, or changing the kinetics of the crystal growth, and then some mechanical removals are used with the scavengers, or with the injecting some fluids to remove those scales, and or dissolve with some chemicals, acid wash, and so these are some effect of inorganic scales. There are some organic scales as well, like wax, in many oils there are wearing some wax. Depending on oil type, we may have some degree of the wax in, and at reservoir temperature, it might be it will be because of the high temperature, it will be flowing with the reservoir, but as the temperature goes down below the cloud point, this will cause the precipitation of the wax in a form of soft solid on the pore walls, or on the even on the tubing walls, and one of the ways to prevent wax precipitation is keeping crude oil warm. There are many ways to keep the crude oil warm, but it is of course difficult for deep water reservoirs, because we to send high temperature downhole, we will have to push this high temperature fluids through the cold water thickness. Also the formations that are usually colder than the reservoir temperature. So in subsea wells, again, long flow lines, sea temperature, etc., etc. Therefore, it's difficult for deep water. It might be electrical warming, but anyway, it's cost and quite technically difficult. There are some inhibitors or to be used in the to prevent the wax precipitations, or again mechanical mechanical removal by scrapping or injecting hot oil, solvents, or acid washing. It's called washing the tubing and wellbore from the wax precipitations. Okay. Asphaltins is another organic material that is precipitation of which is triggered by the pressure change. It is again just like a wax. It's present in the crude oil as a metastable colloidal dispersions, but the pressure change, the pressure decline, may cause those dispersions to precipitate, and it can occur even above the bubble point. So the because it's the heavier part, hydrocarbons, and it's usually found in a specific part of well facilities, and it might be on different locations. It's the difficulty related to the asphaltins is that solid asphaltins is not easily to be redissolved, and if it is kind of getting a solid phase, then it starts aggravating together, and it creates a quite a large, relatively, particles that will cause blockage in the tubing, in the wellbore perforations, and the upper the tubing, reducing the flow path of the fluid to the surface. So, interestingly, the severity of the operational problem not related to crude's asphaltene content. It might be it might precipitate in conditions in terms of the asphaltene content. It might precipitate and aggravate with time. So the total composition of the asphaltene is because of its cumulative effect, the even small asphaltene content of the crude oil may cause some blockages in the flow path. They may have a high heavy metal content, which is again environmentally is and also the solidness of these precipitations are very high, and the in most cases for mechanical removal from wells and facilities are required, like scraping, and it is rarely observed in the reservoir in the formation, but possible, as we said before. And also it's purely soluble by solvents, by any chemical compositions, and even worse, these precipitations may be triggered by acids, particularly if they contain ferrum iron ions. So another type of formation damage mechanism is the pressure reduction. What happens in pressure reduction, as we learned in organic and asphaltene scale problems, increasing formation effective stress, so sand production, compaction of producing interval, fault creation or reactivation. These are extreme cases. And formation permeability reduction, again due to the compaction of producing interval. It will compact also the pore sizes, pore throats, and the permeability will reduce. As we said, multi-phase flow effect due to the below the bubble point or dew points, when the gas dissolves out of the oil or condensate dissolves out of the wet gas, and it leads, as we said, to reduced relative permeability. Where the formation damage during the stimulation, again we talked about that reaction of acids with formation rock and fluids can generate formation permeability damage due to the precipitations, due to the deconsolidation of rock matrix when the injected acid or injected fluids may dissolve the cement of the rock, and in that case the fines or sand particles or rock particles will be detached from each other and become the mobile and moving inside of the reservoir. It will create blockage of the pore spaces, pore throats, and generate the migrating fines, blocking the pores. some acids and some types of crude oil, depending on the proper physical and chemical properties, may create a sludge formation, may form a sludge, which is very high viscosity amorph fluid, and that will again cause the blockage of the flow passes. The same with the viscous emulsion formation and wettability change and water blocks as we start producing water, the injecting water for the stimulation, especially in case of hydraulic fracturing or frac pack. So these water droplets will block the pore spaces in the near wellbore zone. Therefore, in the stimulation, especially acid stimulation, it's very important to select correct or a proper chemical composition for the acids. Okay. So this is the example of formation damage due to the workover operations. So the insufficiently filtered or cleaned water caused the completion fluid or workover fluid caused a decline in the well production, and as time went by, the production almost halved from this well, just because of the wrong designed or wrongly selected completion fluid. Just very simple during this very simple operations of tubing change out. So just changing tubing in the wellbore with the not clean the completion fluid caused this this kind of decline in the wellbore, and it's even had a cumulative effect, and you can see the very drastical drop in the production rate. These are the workover fluid guidelines to how to choose correct. Ensure workover fluid does not react with either minerals that make up the reservoir rock and the aqueous and the hydrocarbon reservoir fluids. So for that we have to first of all have a good understanding of the reservoir rock minerals, chemical composition, and good understanding of the hydrocarbon reservoir fluids and the physical and chemical properties. So, for example, the potassium chloride brine may inhibit clay swelling, so may prevent clay swelling. Use the workover fluid after the careful filtering, so to be solids free and or correctly sized particles to form an external filter cake rather than having the filter cake inside the pore space or pore throats. And also, it's very important that those particles are the soluble after injecting solvent. That means those even if some particles are entered the reservoir, so before the commencing the production, we inject a solvent to solve those particles and produce back them to clean the pore space. So they should be soluble with certain solvents, so we can have a clean perforations, clean flow passes in the formation. Minimizing contamination of the filter brine, use then the completion fluid during the workover, which is the tanks that are contain those fluids should be clean. Lines, pumps, tubulars, everything should be clean time to time, and after each workover operations. Minimum use of pipe tubes in these operations. Using dedicated tanks to reduce the contamination. Again, solids-free brine containing less than 200 ppm solids, and 90% of these solids should be smaller than the average pore size, 10% average pore size. Cover fluid loss by reducing the pressure difference to keep the fluid loss under control. Okay, let's leave it for the identifying the formation damage and estimation, diagnosing of the formation damage for the next lecture. We'll talk about that tomorrow. Any questions about this today's lecture, today's topics? Was everything clear? Can you hear me?
Not everything, but somehow it's clear.
What is not clear? Okay, I will give you time to think about what is not clear on your questions. So form your questions, send them to me either on email or through this Teams channel, and I will consider them tomorrow or other day lecture, and we'll try to answer them so everything is clear for you, which is the aim of this course. Okay, it is very important to understand what you learn rather than memorize and just preparations for the exam. Okay, if you understand it, if that you will remember it for your lifetime, but if you just memorize it, that will not be helpful after exam, useful after exam. Okay, again, go through the material in your textbook, and if you find that you have a questions or areas that are not clear to you, completely clear, then form your questions and get the explanations from myself, or it might be discussed with the whole class, and we'll find the correct answers to the questions. Okay, thank you very much. See you tomorrow.
See you.
So.
See you.